Hi, I am Ibraheem, a freshman in the Mechanical Engineering department at Bilkent University. I am presenting my experiment on the time period of a pendulum. Pendulums are essential in understanding oscillation and motion, and I focused on how the length of pendulum affects its time period. My hypothesis was that the increasing the length would increase the time period, assuming the average velocity remains constant. Here's the setup for my experiment. I used a boss clamp stand, a 50 grams bob, a 50 centimeters string, and a meter rule to mark lengths. The time was measured with a stopwatch on my phone. For the experiment, I used the formula for the time period of a pendulum. This formula tells us that the time period depends only on the length of the string and gravity, not the mass of the bob or the release angle, as long as the angle is small. Longer pendulums take more time to complete an oscillation, which is the core concept we tested. Here's a look at how I conducted the experiment. I marked specific lengths 5 centimeters, 10 centimeters, etc. on the string for precise adjustments. For each length, I displaced the pendulum to a 90-degree angle. This ensured that the average velocity and height remained consistent across trials. After releasing the pendulum, I timed 10 full oscillations and calculated the average time per oscillation. This reduced the timing errors. I measured the time period for each length twice for consistency and minimizing random errors. Then I divided the total time for 10 oscillations by 10 to find the average time per oscillation. Here's the data I collected. When I plotted the time period t against the square root of the length under root L, I found a linear relationship. As shown in this graph, this aligns with the theoretical prediction from the formula of the pendulum, which suggests that the time period increases as the square root of the length increases. Looking at the graph, we can see a clear trend. As the length increases, the time period does as well. However, there's a noticeable y-intercept in the graph, which isn't ideal. According to theory, the graph should pass through the origin, meaning when the length is 0, the time period should also be 0. The presence of the y-intercept suggests that there may be systematic errors or external factors affecting the results. Despite the y-intercept, the overall linear trend still supports the theoretical model. This shows that the relationship between the time period and the square root of the length is valid, confirming the core principles of pendulum motion. While the graph followed the expected trend, I noticed that at 90 degrees, the pendulum occasionally exhibited rotational motion. This caused the time period to increase as the restoring force was no longer linear. This sporadic behavior led to some overestimation of the time period. Therefore, during trials in which rotational motion occurred, the results had to be discarded. In conclusion, my experiment confirmed that the time period of a pendulum is directly proportional to the square root of its length. The results were consistent with the theoretical predictions, despite minor errors caused by the rotational motion and other factors. This experiment not only reinforces the classical mechanics, but also highlights the importance of controlling experimental conditions for accurate results. Thank you for